Welcome back to The Explainer. Today, we're putting on our detective hats to examine what I like to call the ultimate mathematical blueprint. We are diving into a fascinating framework where the total failure of a mathematical rule in a higher dimension actually holds the exact architectural key to proving a massive, long-standing conjecture in a lower dimension. It's a really elegant mathematical paradox, and we're going to map the whole thing out equation by equation. Take a look at the math we have mapped out here. What we're exploring is the Adelic Langlands Program, and specifically how it fundamentally translates the infamous Jacobian Conjecture. At the core of this entire framework is a pretty wild concept. We are taking a known three-dimensional algebraic anomaly, specifically a non-injective Keller map, and we're using that very failure to build a structurally sound, completely bulletproof mathematical solution for the surviving two-dimensional Jacobian conjecture. Basically, we are taking an algebraic disaster and turning it into an analytical tool. Here is how we're going to tackle this today. First, the 3D anomaly, then unfolding the fiber polynomial, gauge connections, the holographic vacuum split, and finally, the two-dimensional vice. You can see our exact roadmap right here. We start in phase 1 by observing a 3-to-1 point collision in 3 dimensions. In phase 2, we mathematically translate this through an automorphic lift, essentially isolating the collision as an uncompensated boundary defect. And then, for phase 3, we get to watch it get completely crushed in 2 dimensions, where the rigid modularity over the ring of Adels guarantees global properness. All right, part 1, the 3-dimensional anomaly. Which brings us directly to part 2, unfolding the fiber polynomial. So how exactly do 3 completely distinct geometric points just collapse into one? To understand that, let's look at the actual governing equation triggering this. Check out the formula. P of t equals c times t cubed minus 2t squared plus b times t minus 2a. Now the variables a, b, and c parameterize the target space. They're the direct outputs. But notice that parameter t. T is acting as our internal coordinator. It's literally tracking the distinct sheets of this non-invertible cover. By isolating that internal coordinator, t, we can watch exactly what happens mathematically when the leading coefficient, c, approaches 0. And I mean really approaches 0. When c vanishes, that entire leading cubic term just disappears, which triggers a sudden and catastrophic structural degeneration of the algebra. We track that whole collapse right here using the discriminant locus equation. The multi-to-one folding behavior is governed completely by this formula. When we calculate this discriminant locus and the polynomial string q hits 0, the sheet count violently transitions from 3 straight down to 1. And this happens precisely at the target coordinate of -1/4, 0, 0. And this perfectly illustrates the fallout of that collision. When the degree of our polynomial drops, those 3 pre-images don't just symmetrically vanish, they actually split. 2 of them stay bounded locally, forming our finite locus, where the Swan conductors register 0 geometric friction, but what about that missing third root? It literally escapes. It shoots off along a unipotent drift line straight to the boundary at infinity, acting as a singular unipotent monodromy defect. Okay, let's move to part 3, translations and gauge connections. So, what happens to that escaping charge? To figure that out, we have to translate our static polynomial into a dynamic geometric operator. It's kind of like compiling raw code into a running program. We start by embedding our algebraic equation into a local Higgs field. Take a look at matrix A. By factoring the polynomial into its monic equivalent to clear out that leading coefficient, we explicitly encode the sheet data right into this 3x3 companion matrix. And here is the really incredible part of this translation. Local flatness perfectly coexists with a global sheet collapse. The math actually protects the local structure, even when the global system is falling apart. The Jacobian determinant remains perfectly constant locally, because that missing topological charge isn't destroying the local volume. Instead, it's being cleanly absorbed by that unipotent drift line at infinity. Next, we lift this into a logarithmic gauge connection. Check out the multivariable covariant derivative at the top. Notice what happens as that leading coefficient c approaches 0, and the poles explode. Localized gauge transition rules step in and actually renormalize the system. The infinity residue matrix shifts into a strictly nilpotent matrix, where n cubed equals 0. So the pole explosion doesn't destroy the map at all. It forms a perfectly stable unipotent monodromy vortex. The Riemann-Hilbert correspondence then steps in to act as an incredible transcendental bridge to compile all of this data. It takes these continuous analytic fields and, through a four-step pipeline using the L-adic tensor lift, structurally compiles them into a wildly ramified L-adic constructible Galois sheaf. Say that 5 times fast, right? Which leads us to part 4, the holographic vacuum split. So what does all this pure math actually look like in physical reality? If we map this out, we can visualize this exact algebraic collapse as an unstable state transition within a holographic vacuum model. Look closely at the top boundary of this holographic screen. The flat affine space is our infrared or IR bulk. The boundary at infinity is our ultraviolet or UV screen. Now remember that unipotent monodromy vortex, our missing third root? It gets stored right there on the UV holographic screen. Because the 3D space has unbounded degrees of freedom at the boundary, this defect just drifts freely. As you vary the internal tracker, this global phase anomaly travels down the renormalization group flow lines and violently fractures the 3D IR bulk, causing a multi-to-1 phase split without ever creating a local singularity. Finally, part 5, the two-dimensional vice. Now you might be wondering, if three-dimensional space can fracture like this, why on earth are we so confident that two-dimensional emergent spacetime is protected? Well, comparing them side by side in this table makes the math pretty stark. In 3D or higher, unbounded boundary degrees of freedom allow that unipotent drift. But in 2D, the Grothendieck-Riemann rock push-forward forces 2D bulk fields to manifest on the boundary curve as extremely rigid weight-2 modular forms. This fault-tolerant modularity of the general linear group just cannot tolerate any localized phase asymmetry. It acts like an absolute cosmic vice, instantly crushing any prospective 2D unipotent boundary twist to 0 and locking the Swan conductor at absolute 0. The math doesn't lie here. That massive pole explosion in higher dimensions, it is not a calculation error. It is a conserved, quantized, topological phase defect securely locked away at the boundary. And it is exactly this mathematically categorized defect that proves the lower dimensions are immune. Because this specific, uncompensated, ununipotent twist is structurally forbidden by the functional symmetry of completed L functions in 2 dimensions, the 2D vacuum state simply cannot undergo that phase split. It automatically quenches the vacuum fracture, officially mandating global invertibility. And in doing so, it proves that the two-dimensional Jacobian conjecture holds absolutely firm. So let's wrap this up with a pretty massive question to ponder. If we know for a fact that a two-dimensional boundary possesses this built-in, absolute mathematical vice that crushes these structural anomalies to 0, yet three-dimensional bulk spaces are inherently unstable to these topological defects, what specific, hidden mathematical mechanisms are writing the source code that protects and stabilizes the four-dimensional space-time universe we actually inhabit? It's something to think about. Until next time, thanks for joining this explainer.